that line, or in this example, this slope vector would be on the same line as your initial described parametric line, but if we added some constants, then it would be off somehow. And all that this slope vector would be is parallel to this line. Now you can do this in 2 dimensions as well, if you want to. You've got a 2-dimensional graph. That looks stupidly 3-dimensional. What the hell? Why does... I think I'm just, like, wired for 3 dimensions now. Let's go like this. That looks does it? That's wrong. That is so wrong. Okay, pretend this is 2-dimensional. I don't know why I'm really thinking in 3 dimensions right now, but you can also do this in 2 dimensions. I'm just going to get rid of that quickly and draw the line up here. You can say the slope vector, if this has a slope of 1, 2, so the slope would be 1/2, your slope vector would have a value of 1, 2. And it's parallel to the initial line, so it can be described as a slope vector. And from there, all you have to do is put it into your delta y over delta x thing, times x plus b. Same thing over here, except now you don't have a fraction, so you have to put it in into each one of these separately to describe how your line changes as you change in t values. Now that we got slope vectors out of the way, let's talk about how to actually find the tangent or the slope vector of a curve. Because obviously here, slope vector was easy enough to find because it was just one big straight line. But in a curvy line, you need to be able to find the slope vector of a curvy line at a given point. At any real point. So in order to do that, all you have to do is, like in Calculus 1, or Calculus 1 and 2, is take the derivative. And all taking the derivative does is it provides you with the slopes of each point. Like, remember how if you have y equals x squared, your derivative dy over dx would be 2x. And all that means is as you follow this y equals x squared graph, the slope of the point, oh my god, I'm really fumbling on my words right now. The slopes at any given point can be described by this graph. And like you can see, as you go up in the positive direction, your slope is going to increase. And as you go in the negative direction, your slope is going to increase negatively, so decrease. So all your derivative does is tells you the slope at a given point, or the slope of the tangent line at a given point. Same thing over here. Taking the derivative of each component will give you the slope vectors at any given point. So if you have a parametric equation of x, y, z, then your taking the derivative will give you dx with respect to t, by the way, dy over dt and dz over dt, which will make your slope vectors at any given point. So you'll get like value, you'll get dx over dt in terms of t, dy over dt in terms of t, and dz over dt in terms of t. And if you're looking for your slope vector at a given point, all you have to do is plug in that value for t, and you'll get your slope vector at that given point. This is your slope vector at any given point. And say you get, after deriving with respect to t, your slope vector is equal to t squared t 1. And you wanted to find the slope vector of this curve at t equals 2. All you do is plug in 2. And what that's saying is that for this curve at t equals 2, let's say that's t equals 2, your tangent line, your slope vector at this point, the slope vector of the tangent line, will have a value of 4, 2, 1. Obviously not really shown accurately in the graph, but that's all that taking the derivative is saying.